Okay, so I want to make a video about a proof technique called mathematical induction. And this is pretty important because it's basically like the fundamental proof concept of computer science. And also it's fairly simple enough that you don't really need to have any mathematical background to be able to understand what's going on. But what I'm going to do is I'm going to explain the concept of mathematical induction and how it works, and then I'll use it in a concrete example to prove a mathematical property. So if things kind of seem abstract at first, just hang in there and I'll tie it together with a concrete example. So say you have a statement of the following form. The property P of n is true for all integers n is greater than or equal to a. So P of n is a mathematical property. It could be, for this video we'll do something simple like an equality, but it could be for all kinds of things, and I'll make more videos of different things that you could prove with this. It has to be defined for integers. So we have this, in our case it'll be an equality, P of n, and we want to prove it's true for all integers n is greater than or equal to a. You can use mathematical induction to do this, and basically there's two steps, the base step and the inductive step, and if you could accomplish both steps, then you've proved the original statement. So what the two steps are is, the first step is the base step. Here you prove that P of n, the statement P of n, is true for n equals a. So basically you're trying to prove it for all integers greater than or equal to a. The first step is to prove it for a. So let's say you want to prove it's true for all integers greater than or equal to 2. First step is to prove it's true for n is equal to 2. Step 2 is the inductive step. This is the tricky part. Here you pick an arbitrary integer and call it k. It could be anything as long as it's an integer. Now you prove that if P of n, the statement P of n, is true for n equals k, then the statement P of n is also true for n equals k plus 1. In other words, if P of k is true, then P of k plus 1 is true. And really, this sounds a little complicated, but what it's saying is that what you have to prove is that if the statement is true for a specific integer, then it's also true for the next consecutive integer. That's what you have to prove. So in other words, if it's true for 3, then it's also true for 4. If it's true for 7, then it's also true for 8. Now, if you can accomplish both the base and the inductive step, you've proved the original statement, this statement right here. Now, why is that? Well, the reason is because in the inductive step, like I said, you prove that if the statement is true for a specific integer, then it's true for the next consecutive integer. In the base step, you've proved it's true for the specific integer a. So you can use that and then apply the inductive step to prove that, since we know it's true for a, then it's because of the inductive step we know it's true for a plus 1. And you can repeatedly apply the inductive step to prove it's true, that since it's true for a plus 1, it's true for a plus 2. Now we know it's true for a plus 2. If it's true for a plus 2, it's true for a plus 3. So let's say you have proved in the base step that it's true for the integer the integer n equals 2. Then you prove the inductive step, which says that if it's true for an integer, it's true for the next integer. You know it's true for 2, which means it's true for the next integer 3. Now you can apply the inductive step again. You know it's true for 3, which means by the inductive step that it's true for 4. And you could go on and on and on till infinity. So that would prove that it's true for all integers n greater than or equal to the base one that you started with. So, if that is a little bit to digest, just pause the video for a second, try to make sure you understand it, and then I'll go through an example. Okay, so here's an example of a statement that I'm going to prove with mathematical induction. So we want to prove that 2 plus 4 plus 6 plus so on and so on and so on, all the way up to 2n is equal to n squared plus n for all integers n is greater than or equal to 1. So this is of the form I was talking about on the last page, where this will be our statement, P of n, that we're trying to prove, and then our base case will be a will be 1, a equals 1. So we're trying to prove the statement P of n for all integers greater than or equal to a, where P of n is this statement equality, and a is equal to 1, the base case. So we'll start with the base step. First we want to prove the base step and then the inductive step. So the base step for n equals a, or in this case n equals 1, So we have our equality that we're trying to prove. 2 plus 4 plus 6, and so on, all the way up to 2n. And this is the left-hand side of our equality. So we'll prove, first we're going to find out what the left-hand side of the equality is for n equals 1. Then we're going to find out what the right-hand side for n equals 1 and show that they're equal. And that'll prove this equality for n equals 1. So here's our left-hand side. Now what does this mean? I think it'll be a little bit simpler if I rewrite it in another way. This is equal to 2 times 1 plus 2 times 2 plus 2 times 3 all the way up into plus 2 times n. So as you can see here, all this is all the integers from 1, 2, 3 all the way up until a general integer n multiplied by 2. So I could even make this simpler and pull out the 2 here. This is also equivalent to 1 plus 2 plus 3 plus n. So basically, you have a sequence of integers from 1 to n, add them all up, and multiply it by 2. That's what the left-hand side of this equation means. So we want to prove it for the case of n equals 1, right? So when n is equal to 1, the left-hand side of that equation is just 2 times 1. But let's say n equals 2. Well, that means the left-hand side of the equation is 2 times 1 plus 2. Similarly, for n equals 3, it's 2 times 1 plus 2 plus 3. And this goes on up until the general case of n. But we only care about the case when n equals 1 for our base case, because what our a is, and that's 2 times 1, which is 2. So for n equals 1, the left-hand side of our equation is just 2. So now we want to check what the right-hand side of the equation is for n equals 1 and make sure it's the same. The right-hand side of our equation is n squared plus n. This is much easier. You just plug in 1 for n. So that's 1 squared plus 1, which is 1 plus 1, which is 2. So the left-hand side of our equation is equal to the right-hand side of our equation, which means we have proven our property, our statement for the base, or our property for the base case of n equals 1. So now we're up to the tricky part, the inductive step. So now we're up to our inductive step. Okay, so in the inductive step, we want to prove that given an arbitrary integer k, if our property is true for k, then it's also true for k plus 1. So we are assuming here that p of k is true, or that 2 plus 4 plus 6 plus 2k is equal to k squared plus k. Basically, we're just plugging we're plugging k into p of n to get p of k. So we're assuming this equality holds. And what we want to prove, we're assuming that what we want to prove is that p of k plus 1 is true. Or in other words, plug k plus 1 into p of n to get p of k plus 1. So we want to prove that 2 plus 4 plus 6 all the way up to 2 of k plus 1 equals k plus 1 squared plus k plus 1. Okay, so this is what we're assuming is true, and this is what we want to prove is true. So let's start with the left-hand side of what we're trying to prove, right? It's this same left-hand side over here, which we draw out in this simpler form. 2 times 1 plus 2 times 2 plus 2 times 3 all the way up until 2 times, in this case, k plus 1, right? So we got 2 plus 4 plus 6 plus, and then you got 2 times k, which is the one before k plus 1, plus 2 times k plus 1. So basically this is just it's just all the integers 1, 2, 3, 4, 5, 6 dot, 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 all the way up until k plus 1, times 2. And I guess I could make this a little more clear by saying 2 times 1. This is 2 times 2. This is 2 times 3. This is 2 times k. This is 2 times k plus 1. So you have your sequence of integers from 1 to k plus 1, all multiplied by 2, summing them all up. And now what we want to do is we want to use our inductive hypothesis, what we're assuming that p of k is true, or that 2 plus 4 plus 6 all the way up until 2k is equal to k squared plus k. And if you'll notice, this is here in this equation, because basically we're saying it's the property 4k, but with the additional term, k plus 1 term. So we could substitute our inductive hypothesis. All of this is equal to k squared plus k, so we could substitute the k squared plus k for all of that, plus 2 times k plus 1. So basically, this left-hand side that we're trying to prove is now equal to this, and the way we got from here to here is by substituting what we're assuming. We're substituting the inductive hypothesis into the left-hand side of what we're trying to prove, and we end up with this. And then we could expand this out. K squared plus k plus 2k plus 2. Here we're just distributing the 2. And I'm going to do some algebraic manipulation, so I'm going to rewrite this in a way that's more convenient for what I'm trying to do. K squared plus k plus 2k plus 1 plus 1. Basically, I'm just splitting up the plus 2 into 2 separate plus 1s. And then I'm going to rewrite this where I rearrange these terms. So I'm going to rewrite it as k squared plus 2k plus 1 plus k plus 1. So basically this is equal to this. I'm just rearranging the order the terms appear, and I'm going to group them with parentheses to make it more clear what I'm trying to do. Now this part right here, this k squared plus 2k plus 1, we can factor that. And what that factors to is k plus 1 times k plus 1, and then we have the plus k plus 1, right? So k squared plus k plus 1, that's k squared plus 2k plus 1, we just factored it. And since you're multiplying the same thing by each other, k plus 1 times k plus 1 is k plus 1 squared. So we could rewrite this one more time as k plus 1 squared plus k plus 1. But wait, this right here we ended up with is exactly what we wanted to end up with, what we were trying to prove. We were trying to prove that this left-hand side is equal to this right-hand side. Well, we started with this left-hand side right here. We substituted our inductive hypothesis, and then we ended up with the right-hand side we wanted to end up with. So we have proved the inductive step. Now, since we proved both the base step and the inductive step, we proved the original statement.